if instead the power is to be at least 525 watts, what must be the diameter of each of the 2 copper conductors in the cord that the young man buys? So it's saying that when you, instead of 470, what is 0.03 watts, that's no good. That's not enough power. So we want it to be at least 525 watts. We need at least that much. So they define these in terms of gauge, right? But it says what is the diameter of each of the conductors inside the wire? So you have your 2 conductors inside the wire, right? Well, we have a formula that's really useful. Resistivity times the length of the cable over cross-sectional area, where the cross-sectional area is defined in terms of pi r squared, which is also pi times d over 2 squared, where d is our diameter, right? D over 2 is radius. Okay, so we plug that in. So then we have d over 2 all squared times pi, which is going to equal L times 4 over d squared pi, right? So that's fairly useful. We want to find d. This is the thing that we're after right here. We know the resistance, right? We know what the resistance is. Actually, scratch that. We need to find that, but that's not important yet. What I'm trying to explain right now is that we have 1, 2, 3 unknowns, but we are told that the material of the conductor is copper. So now resistivity of copper. This is something I actually got stuck on myself. Resistivity, spelled it wrong. Resistivity of copper. It was something I could actually look up. I was stuck on this for quite a long time, and then I remembered that Google actually exists. So then we have 1.68 times 10 to the negative 8 ohm meters is the resistivity of copper. So we can just plug that right in. So now we only have 2 unknowns. Let's solve for D. D is going to equal rho L, 4 rho L, right, over pi times r. This is all under a square root. That's what D is going to come out to be. So now what we're looking for is the minimum size. How small can we have this be when we still get the desired power, right? So in order to have that, we need to have what is the maximum resistance that we can have for this diameter, because this is inversely related, right? This is 1 over R max, so that this goes up, this is going to give us our minimum. Okay, so how do we find R max? Well, we remember that the total resistance of the cable, of the system, actually, the vacuum plus the cable, was R naught plus 2 times RC. And we recall that we used this relationship of total power delivered was delta V over RT, total resistance. So it's total power delivered was delta V over total resistance squared times R naught, right? That's what we used to find the last value that we had for part A. Good. Well, we can also recall that R naught from the beginning was defined in terms of was delta V over power squared. Let me just double check that real quick. I have a lot of squares and p's hanging around, so I don't want to write the wrong thing down. So it's actually not squared. That's delta V squared over p, right? So then we have delta V to the 4th over RT squared 1 over power. Okay, so now this is going to be, the total resistance is going to be the maximum resistance that we need. So this is going to be defined in terms of this total resistance here. This is the thing we need. So with a little bit of rearranging, we're going to get delta V squared 1 over total power times the initial power that we were given. Like this. Okay, and so we also recall that this is equal to R naught plus 2RC. This one takes a little while. So now we have RT max, the total maximum resistance. What we're really after actually is the resistance of the cable, not the total resistance, because we already know this is, we know what this is. We know what R naught is. That's the resistance of the vacuum cleaner. So when I said that it was RT max, it wasn't. This is R max here actually comes from the cable max. So I should write that down. This is R cable maximum, not the total resistance of the system. So we're looking for the maximum resistance of the cable that we can have. So RT max is going to be equal to R naught plus RC, 2 times RC maximum. That's going to be equal to delta V squared, 1 over the square root of total power times the initial power that we're given. Right? Okay, great. So the total power, like we said, this is going to be defined in terms of 525 watts. That's what we want. That's the desired total power, minimum that we can have. And this is the one that we're given. This is the power that the machine is capable of. So now what we can do is we can solve for RC max in terms of things that we actually know. Solve for this thing, because we know these values. We know this value, we know this value, we know all of this stuff. So let's just solve for it now. So then, RC maximum is equal to delta V all squared over total power times the initial power minus R naught. This is all times a half. So we plug all these values in. We now have total resistance where the P sub T, which is the total power, is equal to 525 watts. This is going to be equal to 120 volts squared over 525 watts times 535 watts. This is under square root minus 120 volts squared over 535 watts times a half. We plug all that in and we get a value of about 0.128 ohms. So that's the maximum that we can have. And so then we plug that value into the dmin, the minimum diameter that we had, which was defined up here, right? So then we have this, let's just put it all under 4L rho pi R, pi RC maximum, which is what we just found. So it's going to be 2 times 15 square root of 15, square root of 15 times the resistivity, which was, we had a value for that, 1.68 times 10 to the negative 8 ohm meters, all over pi times 0.128 ohms. So I plug all of this in, just double checking what I did here. And then I get a value of approximately 1.6 millimeters. So if I go through that whole process again, well, I mean, I don't have to go through all of this again. This is a lot. But if we just plug everything in again using now instead the maximum value that we're told, RC max let's do it this way. The next value, PT, is equal to 500 and what was it? It was 532, which gives us an RC maximum. Remember, we had this formula, so we plug that into here. So instead of 525, we plug in 532, right? That is going to give us a value of 0.0379 ohms. And then I plug that into the D minimum. We have 215 and then 1.68 times 10 to the negative 8 ohm meters, all over pi times 0.0379 ohms. That gives me a value of 2.93 millimeters. That's the minimum that it could be in order to deliver the power that we need, which is 532 watts. That's a lot. I mean, that's actually really thick. Almost 3 millimeters is actually fairly thick. I mean, compared to what we had before. If you only want 525 watts, then you only need this size. And so that's an interesting sort of thing because the diameter is going to depend on inversely on the resistance of the material, right? So